we're going to assume that once a router is infected, it stays infected. And why are we assuming that? For the reason that I said at the very beginning, which is the firmware upgrade process on these routers has the sort of unfortunate security side effect of the fact that the firmware upgrade process is itself firmware upgradable. So what does that mean? If I infect you with malware, the first thing I do is I change the firmware upgrade process so that it doesn't accept firmware upgrades from anyone but me in the future. Right? So now you're infected and there's nothing you can do about it. Okay. So what we're going to do is in our dynamics, eventually what I'll do is I'll show you that we simulate with 5 initial random infections on the network or on the giant component. I'll explain that why in a second. Let me get to this. This is the basic. This is a graph diagram of the infection model or the epidemic model. So there's basically 2 places or 3 places you can start. You might start off being removed because you had a WPA encryption. Okay. So if you had WPA encryption, you're just removed to begin with. Otherwise, you could belong in 3 other nodes. You could have a WEP encryption enabled. You could have no encryption enabled and a default password, or you could have a non-default password. Okay, if you have a non-default password, you start in what we call state 1, okay, which corresponds to the idea that we don't know what your password is, we just know it's not default. So we're going to start doing a dictionary attack. Okay, so we said we assumed about 25% of the non-default passwords are weak, so we take the amount of time it takes to do a weak dictionary attack, and with probability 25%, you're going to go to the infected state. Otherwise, you're going to go to state 2, or susceptible 2, where with another 11% probability, you'll go to infected. But now we have to account for the time it takes to do a much bigger dictionary attack. Okay. Now, the third case would be that, no, you still failed on the larger dictionary attack. So that corresponds to you having a very strong password, at which point we're just going to assume that we'll never get into your router. And then you go into removed hidden. Why do we call it hidden? Well, imagine you have your router's under attack by your 2 neighbors, one on your left, one on your right. Right? Those 2 routers can't, we're not assuming they're communicating to sort of optimize their attack. So maybe the house on the left has already tried to attack your router and failed. It hasn't communicated that to all of the other infected routers to say, back off on this guy, you're not going to succeed. So we assume that the guy on the right is still going to have to take time to attack. Yeah?
So hypothetically, though, could you have some kind of triangulation set up?
Yeah, I mean, it depends how much you want to give credit to the malware authors. And I mean, this is just a simulation of a reasonable scenario. Okay, so the only other state you could be at is you had WEP encryption. So what happens with WEP encryption is once you break it, then basically you're back at the case where you have to break the password. So now, once you've broken the WEP encryption, you go to state 1 and you go through this whole password breaking process. Okay, we assume if someone went to the trouble of putting on the encryption that they also changed the default password. So there's only the possibility that they have weak passwords. Okay, so these are the initial possibilities for susceptible routers. You start in no password, a weak password with no encryption, or WEP encryption. Okay. Any questions there about the dynamics? Okay. So what's next here is we have a video where we show the example of one simulation of an outbreak in Chicago. Okay. This is on the network that corresponds to the 45-meter radius communication network. So we look at what happens in 2 days. I'll start it. You see what happens. So what's going to happen is we'll see all the dots, and the red dots correspond to the infected nodes. And okay, it's starting. Corresponding to the infected nodes, and every hour, or is it every 2 hours? I can't remember. We see the progression. Yeah, every 2 hours. So we'll see in 2 days how this progresses. It's a bit slow. But what we see is we see a huge amount of...
so the number that it's hours?
That's the hours, yes.
How many did you see? How many routers?
So we initially seeded 5 routers, and I said I'd come back to that. The reason why we seeded 5 is there's some small chance that an initial infection could just fail because you choose a router that's, say, neighbors with a bunch of really highly encrypted... its neighbors are all really highly encrypted or have strong passwords. So there's some initial chance you could fail out. So we started off with 5 random things because we thought that would be enough. And it was, and then we went down and we actually checked, and with one it fails on occasion, but basically with two it always succeeded in our simulations.
Does it take longer if you have only two, or?
Yes. Okay. But not nearly as much longer as you'd like to think. I don't have the data here, so I can't quote it exactly. Okay, so are we done? Okay, so what we saw is in the first 48 hours, this actually corresponds to about, I think if I remember right, it's about 30,000 routers being infected. Okay. So again, we're not assuming that all routers can be infected, and we're I think, making fairly reasonable assumptions on the attack rates based just on password breaking and WEP breaking. Okay. In fact, in this outbreak, you basically see very little of the WEP effect because we assume that it takes on average 2 days to break WEP. You might say, well, why? I just told you you can do it in under a minute. If you get into the details of active versus passive attacks and what different routers can do, you realize it's more reasonable to assume 2 days. Okay. So we looked at, I mean, I've only got the video for the one city, but we looked at the other cities. So the different things you want to look at is, first of all, how big, as a fraction of the entire city's router population, how big is the giant component? Because that represents how far the infection can spread without really putting effort into spreading it around a lot. And so this changes dramatically between different cities. And of course, this has a geographic component and a security component. Okay, if routers are far apart in, say, more residential areas, then there's, of course, fewer neighbors it can talk to. And if people use more encryption, in particular WPA encryption, we're taking those routers effectively off the graph. So they're shrinking the GPA too, or the giant component too. But we see here different things. Not surprisingly, in most cities, the giant component ends up being in the downtown district. So the two exceptions are West Lafayette and Boston. And there we see them triangulated nicely around the universities. So, I keep saying West Lafayette, but it's actually, I mean, I'm never quite clear how those two cities are separated, but it includes Lafayette as well. And it doesn't surprise me that Purdue has the giant component as opposed to downtown. And in Boston, you see it stretched from Harvard to MIT, right, where all the students live. So we see the size of the giant component. Then we see the total rates of encryption, which, of course, has an effect.
Actually, your map, I can tell you, it's West Lafayette because you see the Wabash. If that's the Wabash, then...
No, it's definitely in West Lafayette, the giant component. I'm just saying that the data, what you're seeing in the picture is the giant component. What the data has is larger. Yeah. Okay. I got to speed up a bit. What time is it again? 5:20.
So now it's 5:10.
Yeah, no.
5:10.
Okay. So here's the results for the other cities. So what we see is what the attack rate is relative to the size of the giant component. So for New York, where you see the green line at the top, and it's about a 50% attack rate, what that means is 50% of the giant component is being infected. Okay? So that doesn't mean 50% of the routers are being infected. I'm not thrilled with this graph, but I didn't have time to redo it. So what you see, though, is that basically the giant... the rate... the infection rate is really just dependent on is more or less going to be 30% for most cities. The outliers are San Francisco and New York, and it's not exactly clear why. But you can basically estimate for a city on average, if you knew nothing else about it, that if you knew what the giant component was, about 30% of them are going to be susceptible. Okay. Okay, so this is a plausible attack, then, we think, and we think it's therefore valuable for the attackers to do, given all the benefits of owning routers that I said before. And it seems like you can actually propagate this attack very easily, given the simulations. So what can we do to stop this from happening? Well, the first thing we can do is we can take advantage of network properties. So one of the things that came out of epidemiology was an understanding of one or two things. So one thing that happens in the real world is that viruses start to spread, and then they just die out and disappear. Okay? And then, but this never happens with computer viruses, and no one was quite sure why, right? I mean, the viruses that were written back in the 90s are still on the network today, and so we have to keep all of the antiviral software up to date, but with all of the previous history.